Hey y'all, today we're going to take Lewis structures one step further and we're going to incorporate some of the lessons that we've learned in the last couple of videos. We're going to look at more complicated Lewis structures this time, and that's going to include Lewis dot diagrams or Lewis structures that have molecules which might not quite obey some of the standard understandings that you've had before. But when we start to incorporate the understanding we now have of formal charge and of resonance, it's all going to start making a little bit more sense. So let's jump right in, and we're going to take a look at some exceptions or oddities to our standard Lewis structures. All right, so the first thing we're going to need to think about in terms of Lewis structures is, what does it mean to have a full valence shell? Now, historically, a full valence shell was generally 2 or 8 valence electrons. So in the past, most of our Lewis structures, the full valence shell resulted in 2 valence electrons, such as for hydrogen, or 8 valence electrons for things like nitrogen or chlorine or fluorine. But right now what I want to look at is an oddity. So we're going to look at a compound, beryllium difluoride. BeF2. Now, when drawing Lewis structures, we actually adhere to the same basic process, no matter what we're doing. So it's not actually a difference in process here. It's more about understanding an odd result than it is about changing the process. So we're going to do the same process. We're going to look at number of valence electrons in the compound. In beryllium difluoride, we have beryllium, which has 2 valence electrons, and fluorine atoms, which each have 7 valence electrons, which gives us 16 electrons total. And we're going to do the same thing as always. We're going to put the least electronegative atom in the center. That's beryllium. And we're going to draw single bonds to the 2 fluorine atoms on either side. That takes care of 4 electrons, meaning we have 12 remaining. We're going to fill the valence shells of our ligands. Now, fluorine does take 8 valence electrons for a full valence shell, so it's going to be 8 for the fluorine. And at this point, I've used all of my valence electrons. But we look at this and we say, wait, beryllium doesn't have 8 valence electrons. It only has 4. It has 2 single bonds. How can this be? Well, the reason it can be is thinking about formal charge. Beryllium in its normal state owns 2 valence electrons, right? So if we think about beryllium, it's in group 2. It's going to own 2 valence electrons. Now, in this case, if we're thinking about formal charge of beryllium, the formal charge on beryllium is going to be 0 because it owns 1 electron from each of the 2 single bonds, which means that the beryllium formal charge is 0 in this case. Fluorine, each of the 2 fluorine atoms also has a formal charge of 0. So if we do the formal charge calculations, beryllium and fluorine would both have 0. Now, if we think about what it would take to give beryllium 8 valence electrons, you'll find that the formal charges actually wouldn't be 0. So let's take a look at what that would be. So if we look at this, beryllium's formal charge in this case beryllium's formal charge would be -2, and fluorine's would be +1. That can't be stable because fluorine is a very electronegative atom. If it's ever going to have a formal charge, it's going to be negative. And the more stable position in this case would be both atoms having a formal charge of 0. So in other words, the formal charges mean that, yeah, beryllium can in this case be stable with only 4 valence electrons in its valence shell. Let's look at another example. In this case, we're going to look at a different type of valence shell, and this is going to be something called valence shell expansion. We're going to use the molecule sulfur hexafluoride as our example. Sulfur hexafluoride. Sulfur has 6 valence electrons. Each fluorine has 7 valence electrons. That means we have to account for 48 valence electrons. It's going to take some time, but we still can do it. We're going to go through the same process. All right. We start with our least electronegative atom in the center. That's sulfur. We're putting fluorines around it. Six of them. All right. We now have just used 12 valence electrons in those 6 single bonds. We have 36 electrons remaining. We need to fill the valence shells of all of my fluorines. We have 0 electrons left, but wait a second. Look at sulfur. Sulfur has 6 single bonds. 6 single bonds. That means 12 valence electrons. How can that be? Well, here's why. Sulfur is in the 3rd period of the periodic table. That means the 3rd row down. That means that it has an empty D sublevel. How do I know this? Well, if we look at sulfur and its electron configuration, it ends in 3p. That means it has filled out to the 3rd energy level. When it fills out to the 3rd energy level, that means that all sublevels within that 3rd energy level exist. The D sublevel simply hasn't filled yet. So as a result, what can happen is there's essentially room, if you want to think of it, for extra electrons because some of those D sublevel electrons can act as valence. So even though we think of only S and P sublevel electrons as being capable of being the valence electrons, in fact, from the 3rd period down, we can have some valence type electrons in the D sublevel. All right, and this is called the valence shell expansion, or we can build out a bigger valence shell than otherwise we would be able to predict. So in this case, sulfur has 12 valence electrons. And if we think about formal charge, it works. Sulfur has 6 valence electrons on the periodic table. It owns half of the electrons in each of the single bonds. That means it owns 1 of the 2 valence electrons in each of the 6 valence, or in each of the single bonds. That means its formal charge is 0. Sulfur's formal charge in this compound is 0. So is the formal charge of every fluorine atom. So this is a stable molecule, relatively speaking. Its formal charges work, even though sulfur has an expanded valence shell. So we've talked about situations where we have expanded valence shells, but also situations where we have reduced valence shells. These can be the case. You just need to make sure you're aware of the fact that it's based on a formal charge understanding. Okay? You can have, anytime you have a 3rd sublevel or a 3rd period or below, valence shell expansion. And the valence shell reduction, well, that's less common, but can still certainly happen, especially with smaller, less electronegative atoms. We're going to look at one more kind of odd or more difficult Lewis structure. That's going to be perchloric acid, HClO4. Now, perchloric acid, if you want to think of it, is really comprised of the perchlorate ion and a hydrogen. Okay, so that's actually how I want to think of it when we're drawing the Lewis structures. Otherwise, it could get kind of tricky to understand how it works. So what we're going to do is we're going to use the base of perchlorate initially. Perchlorate, ClO4 minus, has chlorine and oxygen and 1 extra electron. So chlorine has 7 valence electrons. Each oxygen has 6, and because it's got a negative charge, we add 1 more. 4 times 6, 24, plus 8, all right, that's going to be 32 valence electrons total to account for. Chlorine's the least electronegative atom. It's going to go right in the middle. Oops. Surround it with my oxygen ligands. That's 4 bonds, 8 total electrons. We're down to 24 electrons remaining. Fill the valence shells of my oxygen. That means they each need 6 more. Now, here's the thing about perchlorate. If we look at this, we've used every valence electron. Chlorine has 8 valence electrons. So does the oxygen. So you'd look at this and say, boom, done, perfect. But it's not. The reason it's not perfect is because look at the formal charges. Each oxygen in this structure has a formal charge of -1, and the chlorine has a formal charge of +3. That's not good. So we need to think about formal charge in this structure, okay? And when we think about formal charge in the structure, the way we're going to do it is by, again, trying to reduce the formal charges to as small as possible, as close to 0 as possible. The way we can do that is by using multiple bonds. So what I'm going to do is if every oxygen, I remove a lone pair and add a double bond, the oxygen that I've done that to, the formal charge goes from -1 to 0. So now the oxygen on the left there has a formal charge of 0, and chlorine's formal charge, you'll note, has gone from +3 to +2. So what I can do is this for 2 more of the oxygen atoms. So I'm going to turn their connections to the chlorine into a double bond. So now if we look at it, the chlorine atom in this situation has a formal charge of 0. It has a total of 1 single bond and 3 double bonds. So that's 7 bonds total. It owns 1 out of each 2 electrons within within each bond. Therefore, it owns 7. Formal charge of 0. That's really good. Oxygen, each oxygen with a double bond has a formal charge of 0, and the one oxygen that has 7 electrons that it owns has a formal charge of -1. But oxygen's the most electronegative atom here, so that's not bad. That's actually good. In fact, chlorate is going to experience resonance as a result of this. And so what you're actually going to see is these 3 double bonds kind of migrating around. And so if I was to completely do this diagram for just perchlorate, I would end up having multiple different structures, all right, multiple different structures, 4 of them specifically, where each oxygen ends up being single bonded once and then double bonded each of the other 3 times. I'm not going to do that, though, because remember, we're not just dealing with perchlorate. We're dealing with perchloric acid. So if I look at this, I need to figure out where that hydrogen is going to go. Well, if you look, each oxygen that's double bound can't bond again, not for formal charge purposes. If you do 1 more bond with each oxygen, that's going to disrupt that formal charge of 0. But remember, one of the oxygens had a formal charge of -1, the top one here. And so what it's going to do is essentially we're going to see the hydrogen bond to that oxygen. So when we're looking at perchloric acid, the fundamental understanding is that we start with the perchlorate ion, look for the oxygen with the negative formal charge, look for the oxygen that can accept a bond to the hydrogen, and that's where the hydrogen is going to go. This is a really tricky Lewis structure. And so what you do is you adhere to the rules, but we play the game a little bit. And the way we play the game is by starting with just the perchlorate ion. That's the easiest way to do it. We're going to talk more about acids and bases, especially as we get into later units, but it's really important to understand how they're structured, because we are going to talk about how their structures can then impact how strong or weak they are later in the year. So today we talked about more complex Lewis structures. We talked about both valence shell reduction, but also valence shell expansion, and one of the more complicated Lewis structures that you will ever have to look at or potentially draw. I hope you enjoyed this video. I'll see you in the next one.